Hey kids, and welcome to our next podcast on polarity. Now that we've figured out how to draw these Vesper diagrams, we're going to use these Vesper diagrams and our understanding of electronegativity numbers to figure out if a molecule is polar or not. So let's take a look at what we're doing this podcast. We're going to determine the polarity of a molecule based on simple structural shapes and unequal charge distribution. And we're going to describe bonding as a continuum, basically going from nonpolar entities to completely polar entities, whether it's covalent or ionic. We're going to take a look at all of these. So let's figure out what polarity means. Chemists believe that molecules are made up of charged particles, electrons, and the nuclei. So you guys know in the nuclei, there are protons and neutrons. Protons are positive, neutrons are neutral. So essentially, the nucleus is positive. And you have electrons, which are orbiting the nucleus, and they're negative. And typically, the electrons are attracted to the nucleus because it's a negative-positive thing. Negative and positives, opposite charges attract. However, those electrons found in the valence shell, the very last shell, those valence electrons, they tend to move around. They can move depending on EN numbers. So a polar molecule is one in which the negative electron charge is not distributed symmetrically among the atoms making up the molecule. Thus, it will have partial positive and negative charges on opposite sides of the molecule. And a molecule with symmetrical electron distribution is called a nonpolar molecule. So what that means, kiddos, is if something has symmetrical electron distribution, what we do to figure that out is we could do two things. Number one, we could look at the elements. If the elements are the same, like chlorine gas, for example, chlorine gas is made up of chlorine plus chlorine, two nonmetals. If you take a look at the periodic table and you look up chlorine, you'll see that chlorine has an EN number 3.2. So two chlorines together have each an EN number of 3.2. Because those numbers are the same, there's no pull that's stronger on one side than the other, so the electrons are going to be shared equally in the very smack dab middle. And we know that there's a thing where there's charges is because of water. Okay, the existence of polar molecules can be demonstrated by running a stream of water past a charged object. If we take a look at this diagram here, and we charge a strip or some kind, sometimes an acetate strip does that, or even a long piece of, sometimes not so much metals, but something made out of plastic, and we rub it, we can basically charge it. And we'll notice that if we run water beside it, the water actually bends, okay? And the reason why it bends, take a look at this diagram over here. Let's say that this is negatively charged, as we can see, because there's all these electrons. What's going to happen with the water is because water is polar, they're going to, the polar water molecules are going to rotate so that the positive end attracts the negative end of the thing that it comes in contact with, and then you're going to have this bending of water. And then when scientists look at that, they're like, wait a minute, I feel that this means something. So it's kind of like the Avatar water bending. Probably not, but you know, the same kind of thing. If you're able to change the configuration or the movement of electrons, you can actually bend water. So basically, if this though were positive, if this strip were positive, these guys would orientate themselves so that the negative end is closer to the positive end because of the attractive forces of opposite charges. So I'm going to show you this this table right now, and then we're going to get into it later, where I'm actually going to break down and show you what this means. Basically, all polar molecules have these configurations, and non-polar molecules have these. This is out of your textbook on page 99, but like I said, I'll show you this later, and I'll actually walk you through it just to see why that is, so you can believe me and believe the textbook. Not all textbooks, not everything in a textbook is true, right? Predicting and explaining polarity. So thank goodness for this guy called Linus Pauling. He explained polarity by creating the concept of electronegativity. We talked about electronegativity and EN numbers in section 3.1. So in order to kind of recap, electronegativity increases as you go up or to the right on the periodic table. Typically here, kiddos, nonmetals have high EN numbers, metals have low EN numbers. The higher the EN number, the stronger the pull of that electron. It's like I can pull you away. If I have a metal plus a nonmetal, it's going to be a transfer of electrons. Remember that? It's going to be a transfer of electrons, but within here, nonmetals, we don't have a transfer of electrons. We have a sharing of electrons, but the sharing may not happen smack dab in the middle. Sometimes the electrons are going to be, not sometimes, always, are going to be pulled towards the nonmetal with the higher EN number. So Pauling explained the polarity of a covalent bond as the difference in EN numbers or in electronegativity of the bonded atoms. If the bonded atoms have the same electronegativity, how do we know? We look at the EN numbers. They're the same. They will attract any shared electrons equally and form a nonpolar covalent bond. Nonpolar covalent bond means that they are shared smack dab in the middle. If we take a look at chlorine, chlorine has an EN number of 3.2, 3.2. They're the same, so those electrons are going to be shared equally. If the atoms have different electron negativities or different EN numbers, they will form a polar covalent bond. Polar means one side is more negative. The greater the electron negativity difference, the more polar the bond will be. That is very important. This is so important, kiddos. Let's let this sit with us for a minute. The greater the electron negativity difference, so that's the difference between EN numbers, the more polar the bond will be. This is a very good concept to understand and to actually kind of really get, because I can ask all kinds of questions on a summative assessment on that. I can ask you to arrange molecules from most polar to least polar. All you have to do is just take the EN numbers, okay? And for a very large electron negativity difference, the difference in attraction may transfer one or more electrons, resulting in an ion bond. Typically, the EN difference is going to be higher than 1.7, not always, but how do you know it's going to be ionic? It's because when you have a metal plus a nonmetal. And we know that nonmetals typically have higher EN numbers than metals, so the metals are always going to lose their electrons to the nonmetals. And we use the Greek symbol delta. This is delta to show partial charges. So what does delta look like? You just kind of make an 8, but you don't finish the 8. And then say, hey, this side's more positive. Why is this side more positive? This has a higher EN number, which means that the electron is going to move closer to that, making that side more negative. If one side is more negative, obviously the other side, the opposite side, is going to be more positive. And here's an example of a metal plus a nonmetal. This electron is so attracted to the chlorine. The chlorine has such a strong pull that it is transferred over. If we take a look at the EN numbers, kiddos, for sodium is 0.9, and for chlorine, it's 3.2. So it's a substantial difference. So let's learn how to predict and explain polarity. Pauling liked to think of chemical bonds as being different in degree rather than different in kind. And he came up with this kind of continuum. According to him, all chemical bonds involve a sharing of electrons, with ionic bonds and polar covalent bonds being just the two extreme cases. So here we have nonpolar covalent, right? Which means the EN difference is 0. Things like Cl2, right? If we take a look over here at ionic, okay, ionic is when you have two things. Typically, it's it's a metal plus a nonmetal. And, oh, I forgot the N. And at the highest is an EN difference of 3.3, but usually around the difference of 1.7 or higher, we're going to have ionic substances, but making sure that you look to see if the first one is a metal. Now let's take a look at this. This changes because I've done some research and I see that it's not always, sometimes this changes over here where they say nonpolar is an EN difference of less than 0.4. whereas polar is a difference of more than 0.4. For us, to make it more sense for us, we're just going to say nonpolar is an EN difference of 0, which means it has to be the same number because, like I said, there's all kinds of information out there that doesn't agree with the 0.4 rule. So we're just going to make it easy. Nonpolar would be the same EN numbers. The bonding in substances, therefore, ranges anywhere along a continuum from nonpolar covalent to polar covalent all the way to ionic, where there is a transfer of electrons. For polar covalent bonds, the greater the EN difference or the electron negativity difference of the atoms, the more polar the bond is. I remember saying that just a few slides ago, so obviously you know that this is very important. So let's take a look at some examples here. Does bond polarity mean molecular polarity? Okay, that's really important. You can have a molecule that has dipoles or a difference in N numbers, but the whole molecule itself may or may not be polar. Well, let's take a look at this. The answer, no. Chemists have found that the existence of polar bonds in a molecule does not necessarily mean that you have a polar molecule. What the heck does that mean? I will show you. Don't worry. Carbon dioxide is found to be a nonpolar molecule, although each of the bonds between the carbon and the oxygen is polar. Why? According to Vesper, 2 bonds, no lone pairs, is equal to a linear arrangement. So if I were to draw that out, it would look like this. Remember, even though these are double bonds, you can say that it's just one bond. We'll start showing the bond polarity as arrows pointing to the negative direction where the electrons want to go, and that is going to equal to a bond dipole. So a dipole basically is this arrow, telling you that there's been a movement of electrons. Okay, so how do we do this? We write out the EN numbers, and we're saying, oh, look, the difference here, I'll erase this so it's more clear. Let's take a look at the difference between these two guys, right? 3.4 is higher than 2.6. This oxygen has a stronger pull of the electrons, so the electron is actually going to move towards the oxygen. This arrow pointing towards the oxygen is telling you, hey, this electron is moving towards the oxygen because the EN number of oxygen is 3.4, which is higher than 2.6. And we also, after including the arrow, we also show that there is this movement of electrons to show that this side is more negative. On this side, 3.4 is higher than 2.6, so there's going to be a movement of electrons, and we're going to say, listen, the outside is negative. We don't worry too much about what's happening in the center. Sure, it's positive, but we're always looking at the outside of the molecule. Okay, if the outside of the molecule is negative, and the outside of the other side of the molecule is negative, it's nonpolar. Polar has to be positive end, negative end. Points from lower to higher electronegativity, which we know the arrows are called vectors. In physics, we know about vectors. And when added together, the equal but opposite bond dipoles equals 0. Okay, if this makes sense to you, if you're mathematically inclined, this will make sense to you. What I do is I just look at the outside molecule. The very outside, if everything on the outside is negative or everything on the outside is positive, which I'll give you examples of, then it's nonpolar. The moment you have the outside of the molecule where one part is positive and one part is negative, then it becomes polar. Other than that, it's nonpolar. So 2 negative ends, nonpolar. Nonpolar molecules are ones where the bond dipoles balance each other, producing a molecular dipole, the vector sum of 0. Okay? So let's take a look at the steps. Draw a Lewis formula for your molecule, the Lewis dot diagram, in other words. Use the number of electron pairs in Vesper rules to determine the shape around each central atom. Vesper becomes very important. You cannot tell a substance's polarity with a structural diagram or Lewis dot diagram. You have to use a Vesper shape. Use the electron negativities or the EN numbers to determine the polarity of each bond. Then add the bond dipole vectors to determine whether the final result is 0, which is nonpolar, or non-zero, which is polar. Okay, kiddos, you can do that if you like. What I like to do is I just like to look at the outside of the molecule and say, hey, the whole outside is either all negative or the whole outside is all positive, nonpolar. If one end, even if one little end is positive and the rest is negative, it's polar. Okay, let's take a look at an example. Predict the polarity of a water molecule. Let's take a look here. So first we're going to draw a Lewis dot diagram. There it is. We know that oxygen is the central atom. It has 2 sets of lone pairs and 2 sets of bonding electrons. No problem there. Then what we're going to do is we're going to draw the Vesper shape. Another word for Vesper shape is stereochemical formula. And now we're going to assign EN numbers of the atoms, and we're going to assign also the delta signs, whether it's negative or positive, to the bonds. And then we're going to draw in our bond dipoles. So let's do that. Oxygen, 3.4, has an EN number of 3.4. Hydrogen is 2.2, but you always use your data booklets to figure this out. Okay, so what's happening here is that their electron is going to move to this part of the molecule. So it's going to the 3.4 obviously is higher than 2.2. So, and this is also going to move. The electron is also going to move. So I have to draw those 2 arrows. This top part becomes negative. These bottom parts, kiddos, the hydrogens, become positive because they lost their electron. It wasn't transferred, but it was pulled towards the 0. Let's take a look at the outside part of the molecule. A negative end and 2 positive ends. Not equal, right? 2 positive ends, 1 negative end, polar. Sometimes what you get as well is you get this guy here, just showing overall charge differentiation. You don't need to include that arrow, but you do need to include each dipole between each bond. So the bond dipoles or vectors do not balance. Instead, they add together to produce a non-zero molecular dipole, shown in red. Basically, you have basically when you're adding vectors, they're not equal. This results in a polar molecule and explains the bending in water. The way I do it is I go, okay, positive end, negative end, polar. Here's another practice question. Predict the polarity of methane. So draw the Lewis formula. There it is. Then we have to draw our stereochemical formula or our Vesper shape. Remember, if it's 3D, because this is tetrahedral, you have to show me the wedge and the dashed line. Now what we have to do is we have to draw our dipoles, and we have to actually draw our delta signs to show where it's negative and where it's positive. So I'm going to do that first here. So we have carbon, hydrogen, and I don't know where, it doesn't matter to me where the dash is or where the dash line is. It's all good to me as long as it's there. So carbon has an EN number of 2.6. Hydrogen, I'll do it in a different color, 2.2. Okay, you'll notice that 2.6 is higher than 2.2. So where's the electron going to go? The electrons are going to go towards the carbon. So another thing to think about is this. The pointy end of the arrow is always the negative, okay? So the flat end of the arrow is always positive. So these are all going to go to the center, which means every part of the outside is positive. Positive, 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 positive. All the same, nonpolar. Okay? And let's just read the summary here so that you have a summary that's not overtaken by marker. Notice how the bond dipoles point to the central atom. There are no positive or negative areas on the outer part of the molecule. A tetrahedral molecule is symmetrical in 3D, and 4 equal tetrahedral bond dipoles always sum up to 0. Just what I look at, take a look at the outside part of your molecule, and you'll notice that it's all positive, so nonpolar. So let's take a look back at this table, and let's go through them one at a time. Okay, first one, diatomic with different atoms. Okay, if it's diatomic with different atoms. Now just be careful. Just because you see this always doesn't mean it's always going to be polar. So 2.2 is for hydrogen. Chlorine is 3.2. You have a dipole going towards the chlorine. The chlorine is negative. The hydrogen is positive, polar, right? Let's take a look at carbon monoxide. And we take a look at carbon monoxide. Carbon is 2.6. Oxygen is 3.4. Moves towards the oxygen. This side's negative. This side's positive. Do you see that? But do not be like all super confident, because what happens if you get HAT? Don't be like, oh, they're different, therefore it's going to be polar. Let's take a look at the EN numbers. What? 2.2 and 2.2? Here's an exception, kiddos. This is a non-polar diatomic with different atoms. So just always make sure you double check, okay? All right, so containing nitrogen and other atoms. The other atoms have to be the same. Notice that nitrogen is paired up here with 3 hydrogens. Nitrogen is paired up with 3 fluorines. Okay, so we have nitrogen. Because it has that lone pair, first I'm going to draw the Lewis diagram. This is going to push those hydrogens down to form a pyramidal shape. So I have to draw in that dashed line and that wedge. So nitrogen has an EN number 3.0, 2.2, 2.2, and 2.2. So what's going to happen, kiddos? I'm going to go towards the hydrogen. This whole top part becomes negative because it's all pointing towards the top. This, therefore, is positive. And it's also the flat end of the arrow. The flat end of the arrow is always positive. The pointy end of the arrow is always negative. We have a negative end and a positive end polar. Now let's take a look at NF3. I'm just going to draw the Vesper shape because we know how that works. This time, fluorine is 4.0. Nitrogen didn't change. It's still 3.0. This time, the arrows are pointing toward the fluorine because it's a higher EN number. These are all negative. This is positive. Still, it's polar because we have a positive end and we have a negative end. Polar. Okay, a couple of other examples. Containing oxygen and other atoms. So here's oxygen with only hydrogen, and here's oxygen with only chlorine. The thing about oxygen, remember, has 2 lone pairs. And then we have hydrogen. Remember this shape? V-shaped angular. So if I were to draw it out, looks like this. Okay, so 2.2 for hydrogen EN number. Oxygen is 3.4. Where are the electrons going to go towards? The oxygen. This whole top part is negative. This becomes positive. And guess what, kiddos? It's polar. Do not compare this with carbon dioxide. I'm just going to show you it seems like this is polar, but it's not. So in this case here, we have carbon being the central atom. Now the central atom has no lone pairs. So what do we call this? This is linear, kiddos. Linear. So in this case here, this is 2.6 and oxygen is 3.4. So it's going to move outwards. Now, look at the difference in shape. This outside is both negative. But because of the pointy shape, all of a sudden this part is telling you it's negative and the outside part here is positive. In this example of the carbon dioxide, both sides are negative. This is nonpolar. And this is polar. I know, good times, right? The next one that is always polar, or typically always polar, but we're always going to check EN numbers because only with the EN numbers can we know for sure, is, putting these all in the wrong spot, is this configuration containing carbon and 2 other kinds of atoms. So let's take a look at this guy. Actually, we'll do both. I have carbon, hydrogen, and then chlorine. What shape is that, kiddos? Do you remember? Tetrahedral. So I'm going to draw a tetrahedral really quick. I have carbon, hydrogen. Remember, we have to draw a wedge. Chlorine, chlorine, chlorine. Okay, carbon is, EN number is 2.6. Chlorine is 3.2. 3.2. 3.2. And hydrogen, 2.2. Okay, so let's draw those dipoles towards the chlorine, because this is higher than that. This side is negative. Towards the chlorine, this side is negative. Towards the chlorine, this side is negative. Whoa, 2.2. It's going this way, because 2.6 is higher than 2.2. This side's positive. Let's take a look at the outside. What's happening with the outside, kiddos? Positive. What? Negative, 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 polar. All right, this one's awesome. I'll draw this one out for you. We have 2 carbons, 5 hydrogens, and an OH. So carbon, carbon, hydrogen, hydrogen, hydrogen. Then we have oxygen, right? And we have a hydrogen here. All right, good times. What? Let's draw this out, shall we? Here we have 1 central atom. How many around it? 4, so that's tetrahedral. Then we have 1 central atom. How many around it? I'll use a different color. Tetrahedral. Right? Now, with a different color yet. Here's another central atom. 2 lone pairs around it. You can't see them because the red's there. And look what's around that is this shape. So let's draw this out. Okay, let's add our EN numbers, 2.2. I'm just going to do it once because, you know, if hydrogen is 2.2, every single hydrogen is going to be 2.2. Or maybe I'll draw it out so you can see. And what's oxygen, kiddos? 3.4. And carbon is 2.6. Okay, let's draw our dipoles going towards the carbon, because 2.6 is higher than 2.2. Towards the carbon. Oh, 3.4. All of a sudden we have this going on. So positive, 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 and negative, positive, and positive. Because of this negative end, even though all of these are positive, because of that negative end here, it's polar. Okay, let's do this. Predict the bond polarity of ammonia. Oh my gosh, you know already. It's going to be trigonal pyramidal. And let me just go back. I can even draw it for you. But you know you can probably do it in your head already, right? Let's draw the Lewis diagram first. This is telling you that it's not trigonal planar, it's trigonal pyramidal. These are drawn down. So you get this shape. Little wedge, dashed line, straight line. EN numbers 3.0. Do you know hydrogen already? Yeah, 2.2. Where are the dipoles going to go? Towards, right? So this side is negative. This is all positive. So what is that, kiddos? Polar. Do not confuse this to something like that. Boron tetrahydride. In this case here, we have this. According to Vesper rules, these are going to spread out as much as possible. You get this shape, trigonal planar. Boron has 2.0, 2.2. The dipoles are going to go all on to the outside. Negative, negative, negative. This is nonpolar. There's equal distribution of all negatives around the outside. In this case here, negative end, positive end makes it polar. Okay, do you remember like dissolves like? This is just some FYI. I'm not going to test you on it, just so you know why we even care about polarity. Polar substances are soluble in polar substances. Nonpolar substances are soluble in nonpolar substances. This is super important. And so if water's polar, it's only going to dissolve polar things. Non-polar solvent like an oil is going to dissolve non-polar things. Like dissolves like. Mixing nonpolar and polar substances results in them forming layers with the least dense on the top. This occurs because polar molecules attract each other more strongly, thus they stay close together, including nonpolar molecules. Basically, here's an example. Two clear liquids formed layers in this tube, nonpolar hexane on the top and polar water on the bottom. They don't mix, they don't dissolve in each other because you have a polar plus a nonpolar. Nonpolar dark orange bromide, or bromine I should say, this is nonpolar, was then added. The bromine dissolves in something that's nonpolar. So the bromine is going to dissolve in the hexane. It will not dissolve in the water because water is polar and bromine is nonpolar. Why do we care? Cleaning. Water's polar is useless in removing oil, kiddos. That's why we need soap. So detergents then have long nonpolar sections which are attracted to or dissolve in a tiny oil droplet. The polar end of each of the detergent molecules helps form a polar layer around the droplet which attracts to water, which is also polar, and it actually lifts the oil away. This allows them to pull the oil droplet away from a stained area fabric and hold it suspended in the wash water. So if you're really good at making soap and you use your chemistry brain, you can be actually millionaire. There's some practice questions. Also, there will be practice at the end of your note package. And go back to those structural diagrams and the Lewis dot diagrams, make them into Vesper shapes, and then you can add dipoles to them. Good times. Okay, enjoy your day. Bye-bye.